Okay, so we're looking at average rate of change and instantaneous rate of change. We were just talking about, okay, if you are looking at a distance, you started at the house and you traveled a certain amount of time, and we said 10 minutes, and you got a mile away, could you figure out how fast you were going? And so someone chimed in and said yes. And we know the distance equals 4 times times formula, right? And so we know the distance that I traveled, it was 1, is equal to r times the time that they traveled. Well, this is 1 mile, and we know time, we want miles, so usually we do miles per hour. And so t is in terms of hours. And so we know that they went 10 minutes. And so t equals 10 minutes. We need to convert this into hours. Okay, so we know that there are 60 minutes in an hour. So 1 hour over 60 minutes is the same thing as saying 1. And our minutes cancel, right? And we're left with 1/6. Or, I'm sorry, yeah, 1/6. And so now if I can get r by itself, which is our rate, and I multiply both sides by 6, 6 is equal to r. Okay, so this rate, right, is telling me that the rate that the car or you were going were 6 miles per hour. So, do you think that you were going 6 miles per hour that whole time, the time you left your house and the time that you got 10 minutes or you drove a mile?
Just the average.
So that's just the average, right? That's an average rate of change. You know, you're stopped, you have to start going. And so you're going to be accelerating. You might come to a stop sign and have to stop for a little bit and go. So this is actually the average rate of change. And so a lot of times we're looking at the average rate of change. But maybe we want to look at an instantaneous rate of change. Maybe you want to look at, okay, you know, 1 minute into the drive, I want to know exactly how fast I was driving. And so calculus gives us that tools to be able to do that. So let's kind of review average rate of change. So average rate of change, right? This is the change in your y value all over the change in your x value. And so the average rate of change between 2 points x sub 1, y sub 1, and x sub 2, y sub 2. Another way that we wrote that was denoting the slope between those 2 points, which was the change in our y value, y sub 2 minus y sub 1, all over x sub 2 minus x sub 1. So another way to write that change in your y value, we can denote that by a triangle and a y. So this is the same thing as saying the change of our y all over the change in our x value. So you might have some x value here, you might have some x value here, x sub 2, our point. So this would mean that would be my y sub 1 value. And if I have a point up here, that would be my y sub 2 value. So it's just giving us that slope between those 2 points, the average rate of change. So we can do that, that's fine if we're just looking for that line, the slope of the line. But you might not have a function like that. You might have something that looks like this. So what if we had a parabola? So f of x is equal to x squared. Okay. And so if we wanted to know what's the average rate of change, between, let's say, x equals 1 and 4. Okay, so to do this, it's given us the x value, so we know what the y value of our point is, and so we can do that by plugging that back in for x into our equation, right? And so we have f of 1, and so this would equal 1 quantity squared. And so doing that, we get back 1 squared is 1. Okay, so we know we now have a point when x is 1, y is 1. And then let's look at what's happening when x is 4. We can go back and plug that in wherever we see an x in a function f of x. And we get 4 squared, which is 16. And so here we can see that we have a point at 416. So the change in our y value, so this would equal, I'm going to start with this point, 16 minus the y value over here, which is 1, all over, if you start with this point here for your y value, you have to start with this value for your x in the bottom. So 4 has to go start in the bottom, minus 1. This is our change of x. So 15, 16 minus 1 is 15, all divided by 4 minus 1, which is 3. Be careful here, you want to do order of operations. You can't simplify these 4 and the 16 together, or the 1s. And this would equal 5. So if we look at this, when x was 1 here, y is 1. When x is 4, not really drawn to scale. That's 16. My graph's a little off, but you get the idea, I believe. Okay, but if you look at this, and you look at this slope of our graph here and the average rate of change here, that might not be a great estimate. Let's say we want to find that average rate of change at a particular value. Well, if we want to, if we close down that interval and get it closer and closer to the value that we want, then we can get a more accurate result. So I don't know if you guys remember the difference quotient. And this is something that we'll be using. And it's part of the definition of a derivative, which we'll be talking about probably in a couple weeks. So the difference quotient basically says if you have some function, f of x, and you wanted to find the change of y over the change of x. So let's say you had a point at f of x. And let's say x plus h. So to get the y value, you would go back in here, right, and you would plug it in wherever you saw an x in your function. Well, we don't know what the function actually is, so I'm just going to write it as f parentheses x plus h, end your parentheses, parentheses. So if we look at here the change in x, it's the change of y all over the change of x. we would look at the first y value. Let's look at f of x plus h minus our other y value, which is f of x, all over. I started with my y value for the second point, so I'm going to put x plus h first for my x value, minus the x value of this point up here, which is just x. And so now if I look at this, I can actually simplify it a little bit. This is not a distribution of this f into the x plus h. This is a function of some value x plus h. So I can't distribute that. But notice in the denominator, I have like terms x minus x. Those actually cancel. And so I'm left in my numerator with f of x plus h minus f of x all over just h. So this is also called a difference quotient. You might have remembered doing this either in intermediate algebra or college algebra. Really what this is wanting us to do, again, it doesn't matter what our graph looks like, but let's again look at a parabola. So let's say this was x. Let's just go out here, maybe not that far. And let's say that this distance in here is h. So basically this point then is going to have to be our x value, right, plus our h value. So this value right here will be x plus h. And what we were just doing is we were finding the average rate of change or the difference quotient. You're looking at this. So we're looking at the slope between those 2 points. But if we take our x value or h value, and instead of it maybe being a length of 2, we sandwich it down and we make it a length of 1, and then a length of 1/2, and then a length of 0.25, and then a length of 0.1, that value is going to get closer and closer to here. So now if I chose my h value, just to be in here, right, if this was h, and I looked at this point, and I found the average rate of change, or the slope between those 2 points, I'm getting a better estimate of what's going on with x. And so technically what we're going to be doing is we're going to be making that distance between x and x plus h very, very small. And by doing that, what we're doing is getting the instantaneous rate of change. We're getting that exact change at that particular point. So far in your career, all you've been really able to look at are rates of change of a slope of a line, but we're going to now be able to find a slope anywhere on any particular function, which is pretty darn cool. So that's kind of just the foundation of really where we're going. And let me see if I can. So the points between those 2 lines that you're looking at, that average rate of change, we call that the slope of the secant line. And that line that is joining those 2 points, we call the secant line. If we're looking at that point exactly, and I don't know if this is going to work, exactly at that value, and we look at the slope and find that equation of the line, then we're saying that that's equal to the equation of the tangent line. So let's first look at the average rate of change of the function f of x equals x cubed minus 2x, and we're just looking at it over the interval of 1, 2. And so all we're doing again, we are given the x values. So this interval, this is the interval, so it's not a point. This is saying that x is equal to 1 and x is equal to 2. So we want to look at what are we going to get if we go back into our equation and we plug in 1 wherever we see an x. So doing that, so I'm just going to go in first and just put parentheses wherever I see an x and write everything else out, and then go back in and plug in the 1. So I have parentheses because I see an x here cubed, minus 2, I see an x there, so I'm going to put a parentheses. And now let's go back in and put in 1 wherever we put those parentheses. And so simplifying this down, order of operations, exponents first. So 1 cubed is 1, minus 2 times 1 is 2. So 1 minus 2 gives us negative 1. So we know we have a point at 1 comma negative 1. So we want to do the exact same thing if we plug in 2 wherever we see an x. Okay, so I'm just going to go in wherever I see an x in my equation of f of x. I'm just going to put parentheses there. So I have an x, so parentheses, and that's cubed, minus 2. I see an x, so instead I'm going to put a parentheses. And now I'm going to go in and wherever I see that, I'm going to write a 2. So order of operations, 2 cubed, 2 times 2 is 4, times 2 is 8, minus 2 times 2, which is 4. So 8 minus 4 is 4. So we also have a point, x is 2, y is 4. So average rate of change, we're looking at the change in y over the change in x, or the slope of the secant line there. So 4 minus my y value over here. So 4 minus a negative 1, all over 2 minus 1. So we get our slope is 4 minus a negative, so that's 4 plus 1 is 5, all over 2 minus 1, which is 1. So average rate of change is 5. So let's just extend that a little bit further, and let's find the equation of the tangent line. I'm not sure if I can, let's try. Yay. Actually, no, let's first find part B. Find the equation of the secant line. Between, or on the interval 1, 2. Okay, so recall, if you are trying to find an equation of a line, you need 2 things. And if you don't have those 2 things, you're going to be given enough information to find those 2 things. You need a point and you need a slope. Well, we just found the slope between our 2 points, and we have 2 points, so it doesn't matter which one you choose, but we need to choose one of our points. So there's a couple of ways to find the equation of a line. So recall, and I usually don't use this form, but some of the my math lab, when you go in to get help, it will tell you this way. You have your slope point formula, the y minus y sub 1 equals your slope all times x minus x sub 1. Which notice is the same thing. If I multiplied or divided both sides by this parenthesis, it's the same thing as equal to our slope. Or I tend to prefer doing it this way just because it gets me in a form that it's easier to graph. Remember, you have your slope intercept form. So remember, if you have y equals mx plus b, we actually know 3 of these values. I just need to know what my y-intercept is. We know what our slope is because we found it up here. It was 5. We know a point, so choose one of the points. It doesn't matter which one we do. So if I chose my point that was 1, -1, well, my x value is 1, my y value is -1. So plugging that in, my y value is -1 is equal to 5 times x, which is 1, plus b. So I can solve for b here. So I get -1 equals 5 plus b. Subtract 5 on both sides, you get b is -6. So once we know that, what our y-intercept is, we know what our slope is. We can go back into this equation and plug in our slope and our y-intercept, and then we have the equation of the line. And in this case, it's the equation of that secant line. So let's just do that. So y is equal to our slope, which we said was 5 times x plus b. So plus a -6 or just minus a 6. Okay, so let's say instead they wanted us to go through and they wanted us to find the equation of the tangent line. So that means we actually have to find the instantaneous rate of change. So let's find the instantaneous rate of change. At x equals 1. So we want to know what's happening here. What is our slope when x is equal to 1 on that function? Let me go back up and grab what that function is. Okay, so we found a couple of things. We found that between 1 and 2, that our slope was 5. Actually, let's first start with, let's look at the difference quotient of this. Quotient. I spelled that wrong, sorry. Difference quotient when x equals 1. So I'm basically, instead of this f of x plus h minus f of x all over h, we're going to go back in here and we're going to replace this with x equals 1. You know what that x value is. So I'm going to go back in here and I'm going to look at what is f of 1 plus h minus f of 1 all over h. Okay, so I don't get caught up plugging in an expression instead of a number wherever you see x. So if we go back in here, wherever I see an x, I'm going to leave a parentheses, but a parentheses big enough to add in 1 plus h. And so we're going to just do this piece right here. So wherever I see an x here, so I see an x, I'm going to put a parentheses, I'm going to shoot it, minus I see 2 times x, so I'm going to leave a bigger parentheses. And let me go back in and plug in 1 plus h there. So 1 plus h. And then I have to do minus f of 1 So all this is telling me to do is go back into our equation and put x again. But wherever I see an x, I'm going to plug in 1. And so I have to subtract this off. This is where you need to be careful. That negative is going to have to be distributed to that whole piece after we plug in 1. So let's put brackets there. So plugging in 1 wherever we see an x, we have this 1 cubed minus 2 all times 1. And this is all over this h value. So let's simplify this down. Unfortunately, I wasn't thinking when I'm like, let's just find the instantaneous rate of change. I didn't see that cubic there. It's not too bad, but it's just going to take a little bit of work. So maybe on the side, I'm going to look at 1 plus h times 1 plus h times 1 plus h, because I have to boil that out. I'm just going to do this on the side real quick. 1 plus h times 1 plus h times 1 plus h. So if I distribute first, just a 1 plus h times a 1 plus h. This gives me 1 times 1 is 1 squared. And an h plus an h, which will give me a 2h, plus an h times h is h squared. So now I need to take what I just found, that multiple, and multiply it by the other 1 plus h. So you can distribute. So 1 times 1 gives me 1, plus 1 times h is just h. So now let's take the 2h and distribute it to each term. So 2h times 1 is plus 2h. 2h times h gives me plus h squared. And then I also have distribute our h squared. So h squared times 1, so that's plus h squared. And h squared times h is plus h cubed. Before we go back and plug in what that is, let's just simplify a little bit further and combine like terms. I'm just going to rewrite it in descending order of powers. And so h cubed, that's the only term of the cube. An h squared plus an h squared, those are like terms, gives us plus 2h squared. We have an h plus a 2h, those are like terms, so plus 3h, and then plus 1. Let's go over here and put this in really quick. That piece right here, that is just this. Just that. So let's just rewrite that in. We have h cubed plus
Wait,
2h squared. Yeah.
is that supposed to be 3h squared or am I
Yeah.
3h squared. Did I miss an h squared?
Yeah, because I think the 2h from the first part, and when you multiply that with the second h, it was supposed to be an
Ah,
h squared.
yep. Okay. Thank you for catching that. You're right. So right here, where we were looking at this 2h here times this h here. Sorry, that was 2h. So this is actually 2h squared right here. So that's actually going to change. Let's just rewrite it. I still have just h cubed, but now with an h squared plus a 2h squared, that's a 3h squared. An h plus a 2h, that's a plus 3h. And then we have a plus 1. So you learn that with the binomial theorem, right? Is that the one that does that, where you can expand binomials to a certain power? It's been a long time since I've done that. I think the pattern that you'll see, and that's one of them. Okay. So I'm just going to go back in, and I'm going to replace that 1 plus h cubed, what we just did on the side over here. So we have h cubed plus 3h squared plus 3h plus 1. At the same time, let's distribute this to -2 and write it into the parentheses. So we would get a -2. A -2 times a positive h is -2h. And then maybe a little side work over here. Inside this bracket here, we have a 1 cubed, which is 1, minus 2 times 1, which is minus 2. So this 1 minus 2, I normally don't work like this, is negative 1. So this negative times negative 1 is really a plus 1. Let me just see, yeah. All over each. Okay, so let's combine like terms in our numerator. We have no other term with a cube, h cubed, so let's just rewrite it. We have a 3h squared, there's no other h squared, so let's just rewrite it. We have a 3h minus a 2h, that's a minus h. And we have a 1 minus 2 is negative 1, and negative 1 plus this 1 over here cancels all over h.
Is it a minus or a plus h?
Let me just go back. You're right, plus h. Positive 3h minus 2h is a plus h. So notice also that your numerator, all those terms in the numerator have an h in common, so you technically could factor the h out and then simplify with the h in the denominator. And we kind of think about it, you're dividing by a monomial, so you can think about h cubed divided by h, you have to divide each one, which is an h squared plus, so 3h squared divided by h, that would give us a 3h, plus h divided by h, which is 1. Okay, so let's kind of just go back and talk about that original equation really quick that we were looking at. Remember, we were looking at the average rate of change between 1 and 2. Well, if you're looking on that and you're looking at 1 and 2, what is that value of h? So if I have x equals 1 here and I have x equals 2 here, I don't remember. Oh, well, the slope we saw was 5. We saw that the slope in here m was 5. What is this value of h in here? Basically this value, right, in between our points, 2 points is 1. Remember our slope is 5 between those 2 points. If we go back in here and plug in 1 for x, notice what you get. H squared is 1 squared. So when h equals 1, we got 1 squared plus 3 times 1 plus 1, which is 5. So we could find the average rate of change, technically, if we make that value of 1, that h value smaller and smaller and smaller, going to 0. This is going to be really helpful. So we want to see what's happening at this. I'm going to go in, and we're going to look at this h squared plus 3h plus 1. And we're going to see what happens to this function h squared plus 3h plus 1 when that h value gets smaller and smaller and smaller. So let's see what's happening when we plug in a half, what happens when you plug in a quarter, a tenth, a hundredth, etc. Can we see if that's going to any particular number or not? And so this is where a graphing calculator is helpful, because they have some tools that you can do that. Or this is also where that Desmos.com is really helpful. And so Desmos, I'm going to go to the math tools, and we're going to go to the scientific calculator. So all we're going to do is we're going to go in there and we're going to plug in our function. So f of x, I put x. I guess we could plug in h if you want, just to be consistent. So this was equal to h squared, so I can get into the exponent here, plus 3h plus 1. So let's see what's happening. We saw f of 1 rise 5. Well, what about half? That gives us 2.75. So I'm just going to see, is this going to approach some value as I make that h value, that distance, smaller and smaller and smaller. So if I do 0.25, I get 1.8. If I do f of 0.1, that's 1.31. So this is really tedious, like I'm saying, if to have to go back in and plug that in and simplify each time. So 1.03 if I plug in a hundredth. So if I plug in a thousandth, actually I went too far for thousandths. So does this number right here, as our h value is getting closer and closer to 0, does it look like this value here is going to a particular number? So if I put in lots of zeros in here, it's rounding. But notice it's going, or it's getting closer and closer to, and it's becoming 1. So we just actually found that instantaneous rate at x equals 1 of our function f of x. Let's just go back and finish. And so I'll show you notation later on how we would do that. We're almost done. So we just found that the instantaneous rate of change at x equals 1 is 1. So if you're looking at the equation in the graph and you want to find the equation of the tangent line, the line is the line that's going through that point with the slope, that slope at that point. We have what our slope is. Our slope is 1 in this case. And we know x is 1. If you remember when we plugged in f of 1 before, I believe we got negative 1 back. So we have a point at 1, negative 1. So again, I'm equation the line, you need a point and a slope. And then we have it. You can find out what b is or use your point slope formula, whatever you feel best doing. So I tend to like y equals mx plus c. If I plug in y, I have negative 1 equals my slope. This time is 1 times my x value, which is 1 plus b. So I get negative 1 equals 1 plus b. Subtract 1 on both sides, b is negative 2. So y equals my slope 1, so 1 times x, which is just x, minus 2. This is the equation of the tangent line. Okay, so let me just write those down real quick, and I just want to show you the graphs, and then we'll stop right there. So we have y equals x minus 2. We saw the other one, the slope of the secant line was y equals 5x. And 5x minus 6. The function was x cubed minus 2x. I'm just going to graph our first function that we were given. So I don't have to put f of x here. It knows that I'm graphing an equation. So x cubed minus 2x. So this is what we were looking at. Let me zoom it in a little bit because we were looking at the slope here, right, between x equals 1 and x equals, what was it before? It was just 2. So x equals 1 and 2. So from right here, oops, I can't really draw on it. So down in here and then up in here. So let me, the equation of our secant line that joins those 2 points, that line, that was y was equal to 5x minus 6. And now let's look at what's happening at 1. And so if I look at the graph of the tangent line, that's y equals x minus 2. So directly at this point here, this is the instantaneous rate of change here is 1, and this is the equation of our tangent line. So that is pretty much an average rate of change and kind of getting you into what instantaneous change is. And we'll look a little more at this tomorrow.